fourth period. We don't want to write the repetition of Monday word. Similarly, Monday first period, Tuesday first period, Wednesday first period. I don't want to write the repetition of the word first. We try to avoid repetitions. So you can store within very small place the information instead of writing as a story. Another advantage is if you have written the timetable as an English story, Monday first period to Saturday last period. If somebody asks you what is third period of Thursday, you have to read the entire story to get the information from it. Suppose if you arrange in rows and columns, you can easily get the information. Therefore, you have two advantages of matrices. One is it occupies minimum space. The another is retrieval of information becomes very easy to you. Okay, in matrix algebra, what we do is big arrangements we denote with symbols like capital A, capital B, capital C, like it, and we perform calculations with the symbols. Finally, we interpret the results. Okay, now coming to the topic. Of course, I start with the very basics. Sometimes you may feel bored, but you will realize the basics which you don't know in between. Now coming to here, matrix. It is a rectangular array arranging in rows and columns. We denote capital A, Aij. Here I stands for row, J stands for column. For example, this is a matrix. What is the order of this matrix? Yogi, please. What is the order? What is the order of this matrix?
M into N, sir.
I am asking order of this matrix.
Ma order of the matrix ma respond amit ma students.
3 into 4.
3 cross 4.
3
into 4.
Cross 4.
Very good, very good. The order here is 3 cross 4. 3 cross. We have 3 rows and 4 columns. Now retrieval of information A 2 3. Second row, third column. It is this minus 4. What is A 3 2? It is this 6. Third row, second column. You can retrieve the information like this. Next. Types of matrices. To remember easily, I am classifying 3 types. The first one depends on order. Depends on this order means number of rows and columns. Init 1, row matrix. We also call a row vector or simply vector. An example to it is 2 minus 3, 7, 6. It contains only one row. Its order is always 1 cross n, any number of columns, but only one row. The next one, column matrix or column vector. It contains only one column. Its order is of the form. Its order is of the form, please. What is the order? Anyone, please?
M cross 3.
M cross
3.
1.
Huh?
It's
1
general. M
Yes,
cross
yes.
1. Very
3 cross 1.
M cross 1 type. Okay. It looks as M cross 1. You have only one column. Next. Horizontal matrix. It looks horizontal. Looks horizontal means it should be like it. Horizontal. When do you say matrix is horizontal? It looks horizontal. How do you define horizontal then? Anyone? A horizontal matrix is of order M cross n, but number of rows.
N less than N.
Very good, M, very good, very good. M less than. Order is M cross n, in which M is less than M. That is horizontal matrix. What is vertical matrix then? Its order is M cross n, in which
M greater than N.
M greater than. Very good, very good. It looks vertical. If those two are equal, what we call?
Square matrix.
Very good, very good. Square matrix. It is a square matrix. Therefore, a square matrix order instead of saying m cross n, we simply say order n. Order n means it is a square matrix of order n cross n. We simply say order n instead of m cross n type. Order n means n cross n square matrix. Whenever you have a square matrix, you can talk about the word trace. Trace means sum of diagonal elements. Please observe, this trace word we use only for square matrices. Sum of diagonal. In particular, you have two diagonals. Here, one diagonal, another diagonal. This is called principal diagonal. And the sum of these means that in this example, 2 minus 4 plus 7, which is 5. This 5 is trace of this matrix. Next. First type over depends on order, row, column, horizontal, vertical, square matrix, and another word trace. Trace is defined only for square matrices. Next, number 2, capital number 2. Depends on elements. We classify the matrices. Triangular matrices. Triangular matrices. It looks as a triangle. Observe it. Matrix, you should have rows and columns. Here, these blue color are zeros, means there is no information here. Means your information entirely within this triangle. And another one, your information is within this triangle. I will show that to you. Your entire information is within this triangle. It looks as a triangle. There is no information here. We call it as triangular matrix. It also looks as a triangular. It is also triangular matrix. In particular, this is called lower triangular matrix. This is upper triangular matrix. Now, I require the notation. When do you say matrix is lower triangular? Can anyone tell? When do you say matrix is lower
I less
triangular?
than J.
I less than?
J.
I less than J? You
Yes,
want to write program, for example, when it looks, it clearly appears to us triangular. But how do you write program? You should write in notation. I less than J. What happens then? The entries we denote with Aij. Aij. Aij values here 0. Aij values here 0 means this 0 is in first row, second column. It is in first row, third column. I value 1, J value 2. I value 1, J value 3. Means whenever I is less than J, these are zeros. Okay. Therefore, a matrix is said to be lower triangular if its entries Aij is 0 for I less than J. It's meaning these three are zeros. Okay, Aij equal 0 for I less than J. Then we say that the matrix is lower triangular. Now tell me upper triangular. When do you say matrix is upper triangular?
I greater than J.
Okay, what's your name, please? Please interact. I appreciate you, please. What's your name? Please.
Sheikh Sakinavi, sir.
Sheikh
Sakinavi.
Sakinavi. Okay, right. Very good. Very good. Please. Okay, you told me I greater than J, but please tell me completely. When I greater than J, what happens? The entries are zeros. Therefore, you should say Aij equal to 0 for I greater than J.
The
For I greater than J. You should completely tell like this. Okay. Aij values are 0 for I greater than J. Right. Next. Here, triangular matrix means either lower triangular or upper triangular. We call triangular matrix. Next. Diagonal matrix. You know diagonal. It is a diagonal. Your information is entirely along diagonal. When do you say matrix is diagonal? Please tell me now. What about Aj? Aj equal to 0. Whenever I less than j, also I greater than j. It's a diagonal matrix. Next, therefore, a diagonal matrix is a lower triangular matrix. Also, it is upper triangular matrix. A matrix which is both lower triangular and upper triangular is called diagonal matrix, in other words. Next, scalar matrix means it is a diagonal matrix in which the diagonal element remains same element, because it can be written as 4 times unity matrix. Next, suppose this element is 1, we call unit or identity matrix. In particular, I2 means second order unit matrix. Similarly, I3, this is third order unit matrix. Suppose these are also zeros, we call zero matrix. Zero or null matrix. We denote, for example, it can be rectangular also. O 2 cross 3 means 2 rows, 3 columns. These are the types of matrices using the entries: lower triangular, upper triangular. Diagonal matrix, scalar matrix. If the scalar is 1, we call unit matrix. If these are also zeros, we call zero matrix. If you observe, never say a rectangular matrix is triangular. This triangular, diagonal, scalar, unit, all these are square matrices only. We use these words only for square matrices. Whereas zero matrix, it can be square or rectangular. Next, the third type depends on operations. The first one depends on order. The second one depends on elements. The third one depends on operations. Operations, already explained to you. Plus, minus, those are operations. Now, first I define an operation, later I come to the classification. Now, observe this one. Operation. It is an operating machine. Input, output. It is a mission, operating mission. Input, for example, the mission name is plus, operating mission. Input 2 and 3. What is the output then? What is the output?
5.
5. Very good. Input, output. Plus is an operation, operating mission it is. Okay. Now, coming to this one, transpose. Transpose is an operation. Suppose A is the input, M cross N matrix. Then the output is another matrix, A dash, A, J, I, N cross N. A is the input, output A dash. Let me explain with an example. Suppose A is the input, then the output we denote with A dash, which is, what's this? What is the transpose of this? A, J, I, the first row 1, 2, 3. Here it comes as column 1, 2, 3. And the second row 4, 5, 6, it comes as column. This is the output. Input, output, and the name is transpose. The mission name is transpose, please. Transpose is not a type of matrix, please. Transpose is an operation. It converts a matrix to another matrix. Okay, this is A. This we denote with A dash. Next, using this operation, we classify the matrices. The first one, symmetric matrix. Suppose the input and output are same for the operation transpose. Means suppose A transpose is A. Such a matrix is called symmetric matrix. For example, observe this. I have given 3 cross 3 matrix. Here I framed a bit. 2, 4. This is not given. Let us assume X. Next, let us assume this is Y. Y 1 minus 8. Next, 5. It is not given Z. Z minus 7. Please, I am asking a bit. A matrix given here X, Y, Z. What are X, Y, Z values so that it is symmetric matrix? Now tell me X value so that it is symmetric. Anyone please? What is X
5,
value?
sir.
X value 5. Very good. What
Yes,
is
sir.
Y value? Y value. This one. Y value? 4. Very good.
4.
What is Z value?
-8.
Minus 8. Very good. Very good. Okay. I framed a bit here itself, please. A symmetric matrix means A transpose is A. In other words, when you fold along the diagonal, every element overlap with the same element. 4 overlap, 4, 5 overlap, 5, minus 8 overlap. 1 overlap, 1 only, 2 overlap, 2, minus 7 overlap with minus 7 only. Okay. Next. Skew symmetric matrix means skew symmetric. A matrix is said to be skew symmetric if A transpose is minus A. An example to it. Observe this. Now, these are zeros, please. Now, tell me X, Y, Z so that this is skew symmetric. Now, tell me what is X value so that it is skew symmetric.
-5.
Very good, very good. What is Y value?
-4.
minus
Very
4.
good. What is Z value?
8.
Minus 8, sir.
It is plus 8, right? Very good, very good. Now, a matrix is said to be skew symmetric when you fold along diagonal, every element overlap with its additive inverse. 8 minus 8, 4 minus 4, minus 5. What about, why this is 0? 0 overlaps with minus 0. Every element should overlap with its additive inverse. If it is not 0, it is not skew symmetric, please. If the diagonal element is, any one of these diagonal element is non-zero, it's overlap with minus of that. Therefore, in a skew symmetric matrix, the diagonal element should be zeros. I think you got one point. Next. Okay, I remove this operation here. The next one. Orthogonal matrix. You know the word orthogonal, the perpendicular. Now here orthogonal matrix means, when do you say matrix is orthogonal? When do you say matrix is orthogonal? Anybody knows here? When do you say matrix is orthogonal? When do you say two lines are perpendicular? When do you say two lines are orthogonal? If the angle between them is 90 degrees. Okay. Right. When do you say matrix is orthogonal? You know it?
A transpose is equal to
A into?
A transpose is equal to I.
Very good, very good, very good. A into A transpose is I, or I am writing in another way, A transpose is A inverse. A transpose, A into A transpose is I, nothing but. A transpose is A inverse. An example, or we write it as same as A into A transpose is I equal A transpose into A. Okay, an example to it. Now observe, just by observing the matrix, we cannot say it is orthogonal. You should test it. You have to calculate its transpose and also find its inverse matrix, and they are equal. Okay, if you don't know inverse, take the transpose of it and multiply with it. It is the given matrix A. Calculate its transpose and multiply with it. You will get I. That's why it is orthogonal matrix. Please observe. So far, I have given matrices with the numbers, but I have given here matrices with functions. When I ask matrix arrangement of rows and columns of numbers, it need not be numbers only. Please, for example, here theta equal to 0, you will get one matrix. Theta equal 45, another matrix. Theta equal 20 degrees, another matrix. I have given many matrices. All those are orthogonal because A into A transpose is I. Now, I want third order orthogonal. Please observe this. It is a matrix of 2 cross 2. Again, same matrix I have written. Let me give the third order orthogonal matrix. Observe 0, 1, 0. If you write like this, 0, 1, it is third order orthogonal. Suppose a matrix given like this, to test it is orthogonal, just take the 4 corners. If this is orthogonal, automatically this is orthogonal. Now, if you observe, A transpose is A, symmetric. A transpose minus A, skew symmetric. A transpose equal A inverse, we call orthogonal. Next. Now, let me give another operation. Conjugate. Conjugate, GAT gate, graduate aptitude test engineering. Okay. What is conjugate? Conjugate. Suppose A is the input, A equal Aij, then A bar equal Aij bar. Let me explain with examples. Now my entries can be complex numbers. Here this I stands for root of minus 1, 2 plus 3i, 4i, 2, 5 minus I. A matrix given. Now I require another matrix using the operation conjugate. The conjugate. If A is the input, then the output, A, we denote with A bar. Just entries conjugates. If x plus iy is an element, x minus iy is its conjugate. It just replace I with minus I. Therefore, its conjugate is 2 minus 3i, minus 4i, 2, 5 plus I. Just replace I with minus I. Now, this 2, don't write minus 2, please. You can think 2 as 2 plus 0i. Here, this is 2 minus 0i. To satisfy ourselves, I am telling this like this. 2 plus 0i, 2 minus 0. This is 0 plus 4i, 0 minus 4i. Okay. This is conjugate operation. Next. Another example. If A equal to 1 minus 2, 4, 3. Now tell me what is A bar? What is A bar?
Same matrix, sir.
Same
Same
Very
matrix,
good.
sir.
Very good. Very good. A bar equal to, you will get the same matrix. 1 minus 2, 4, 3. Bar, A bar equal to. Now observe this note. A is real if and only if the short form A bar equal to A. Observe it. If these two are equal, then we say that such a matrix is real matrix. Means you have only real entries. A matrix is said to be real if and only if its conjugate is itself. If A transpose equal to A is symmetric matrix. If A bar equal to A is a real matrix. Means A bar. After going to bar, he is coming out without bar. Okay, such a person is real. Okay, without bar. After coming out bar also, he appears as normal. Okay, such a person is real. Okay, A bar equal to A. Next. Conjugate transpose, another operation. The name itself, conjugate and then transpose. We denote with power theta, A bar and then transpose. An example, suppose I have taken the same matrix A. My operation is theta now. We call conjugate transpose. Then what is A power theta for this matrix? Now tell me this. What is A power theta? Take its conjugate, then transpose. What do you get? Tell me this, please.
Minus 3i.
First entry, 2.
2 minus 3.
2 minus 3.
Second entry, first row.
2.
2. Very good, very good. The transpose of this one. The transpose of this one.
Minus 4i.
Okay, the transpose of that. Okay, clear?
ఆపేసాను కదా.
Okay, this is a power theta. Conjugate and then of course this is same as transpose and then conjugate. First take transpose, then conjugate. It remains same. To denote the power theta. Next, the fourth one. I have given symmetric, skew symmetric, orthogonal matrices. Now, Hermitian matrix. A matrix is said to be Hermitian if its conjugate transpose is itself. Conjugate transpose is itself. An example. A matrix given. Here, I'm asking to fill these gaps so that it is Hermitian. Now tell me the entry. First row, second element, the middle element. What is this element? So that it is Hermitian. Now tell me this element, please. Any one of you?
4 minus 2i.
4 minus 2i. Very good. You will get conjugate of this element. Transpose. Transpose and the con. 4 minus 2i. Very good. What is this element? The first column last. What is this element? What is this element, please?
5 plus I.
5 plus I. Very good. What is the next element?
8.
8 only, please. 8 plus 0i, 8 minus 0i to satisfy ourselves. I am telling as 8 minus 0i. Okay. This is a Hermitian matrix. Now, every element overlap with its conjugate element. When you fold along diagonal, 4 minus 2i, 4 plus 2i, 5 minus I, 5 plus I, 8 plus 0i, 8 minus 0. Please, 6. 6 overlap with 6 only because 6 plus 0i overlap with 6 minus 0i. That's why in a Hermitian matrix, its diagonals should be only real numbers. If at least one entry is not real, if you have I term in it, it is not Hermitian, please. Okay. Diagonals are real in a Hermitian matrix. Let me prove this. Suppose x plus iy is diagonal element of Hermitian matrix. X plus iy is diagonal element of Hermitian matrix. Then its bar, its conjugate is x plus iy. Please, how I have written, please. Suppose x plus iy is diagonal element of, many of you may be confused here, x plus iy bar is x minus iy, but I have written x plus iy. Here my intention is, I have taken a Hermitian matrix and in it I have taken diagonal element because mine is Hermitian matrix and I have taken diagonal element. Therefore, in a diagonal element, conjugate transposes itself. Conjugate transpose remains its place in diagonal. Transpose won't affect on diagonal elements. Therefore, power theta means conjugate, then transpose means it's same. The left side, right side, the same element. X plus iy is x plus iy bar because A is Hermitian. Then the left side is x minus iy equal to x plus iy. It should happen. Now both sides you can cancel x are 2iy equal to 0. Therefore, y value 0. Therefore, whenever x plus iy is diagonal element of Hermitian matrix, I assumed Hermitian. Whenever x plus iy is diagonal element of Hermitian matrix, then this y value should be 0. Means it is a real mat. It is real. Diagonal element of Hermitian are real. Okay, next. skew Hermitian matrix. When is a matrix skew Hermitian? Please, you know, symmetric A transpose is A. Skew symmetric A transpose is minus A.
A power theta equal to minus A.
Very good, very good. A power theta now. Conjugate transpose is minus A. Right, very good. Now, I have given a matrix again. Now, it is a skew Hermitian matrix given to you. Now, fill these gaps. Now, tell me this element. What is this element? So that it is skew Hermitian, please. What is this element?
6 minus 2i.
Minus 2i.
6 minus
2i.
it is
2i.
wrong, please. Wrong, please.
Minus 6 plus 2i.
Very good. Minus 6 plus 2i. Please, A power theta equal to minus A. Because transpose helps us to identify the place. Here, this element comes from 6 plus 2i. How it is coming? Minus of conjugate. Minus of conjugate. Therefore, minus 6 plus 2i it is. Now tell me this element now. In second row last. What do you get?
9.
Plus 9. Very good. Plus 9. Plus 9. Now tell me this element. Third row first.
Minus 3i. Minus
Min-
3i.
Minus 3i.
3
Plus
3i.
3i.
3i only, please.
3i also.
3i only. I think you got it. Therefore, only conjugate minus of conjugate. Minus of conjugate. What is the conjugate of 3i? Minus 3i. Minus of conjugate plus 3i again. So the real 6 plus x plus iy becomes minus x plus iy. Okay. Now, in a skew Hermitian matrix, the diagonals are pure imaginary or 0. Please observe. Why? Why this? Observe it. Suppose x plus iy is diagonal element of skew Hermitian. Then, because of diagonal, it won't affect transpose. Its conjugate should be minus of it. Its conjugate should be minus of it. Its conjugate is minus of it using this. Therefore, the left side x plus iy bar is x minus iy, right side minus x minus iy. Now, both sides you can cancel minus iy. Therefore, 2x equal to 0. Implies x value 0. Means if x plus iy is diagonal element of skew Hermitian, then x value should be 0. Means you remain with I times 2, I times 0, I times minus 4. Means the diagonals are pure imaginary or 0. Because 0 you cannot call imaginary. That's why pure imaginary or 0. In other words, in complex plane, real axis, imaginary axis. Hermitian matrix, the diagonals are on real axis. In skew Hermitian, the diagonals are on imaginary axis. The next one. This is about Hermitian and skew Hermitian. Now the sixth one. Unitary matrix. Please, it is not unit matrix, unitary matrix. A power theta equal to A inverse. Or this is same as A into A power theta equal to I equal to A power theta into A. Okay. An example to it, of course, directly by observing we cannot tell. Each entry by 2 it is. Calculate its power theta, then multiply with it, you will get unit matrix. So it is unitary matrix. Unitary matrix, you are getting unit matrix. Unitary matrix. So A power A transpose equal to A symmetric, A transpose equal to minus A skew symmetric, A transpose equal to A inverse orthogonal. Now here A power theta equal to A Hermitian, A power theta equal to minus A skew Hermitian, A power theta equal to A inverse unitary, it is same as this. Okay. Now, suppose these two are equal, the result may not be I sometimes. Normal matrix means, suppose A into A power theta and A power theta into A are equal. A matrix given A into A power theta and find its conjugate transpose and multiply within reverse order also. If those are equal, such a matrix is said to be normal matrix. Please observe, every unitary matrix is normal because unitary matrix is these two are equal, also equal to I. But normal matrix need not be unitary because the result may not be I always. I think you follow. A matrix is said to be normal if A into A power theta equal A power theta into A. A matrix is said to be unitary if A power theta equal to A power theta into A equal to I. This result also. Next. Involutory matrix. A matrix is said to be involutory if A square equal to I. A into A is I. Such a matrix is said to be involutory. For example, unit matrix is involutory. I square equal I. Idempotent matrix. A matrix is said to be idempotent if A square equal to A. You are getting A. A equal to A. A equal to A. Such a matrix is said to be idempotent. Unit matrix is both involutory and idempotent. I square equal I. Next. Periodic matrix. Period. Period means, for example, Sunday to Saturday. Again Sunday to Saturday. Sunday to Saturday. It is a repetition. Similarly here, A power k plus 1 equal to A. If you go on finding A square, A cube, A power 4 and so on, sometimes you may reach again A. Sunday, Monday, Tuesday. Again you are getting Sunday. Similarly here, again you are getting A after some stage. If you get A again like this, such a matrix is said to be periodic matrix. Okay. For example, Sunday to Saturday. After 7 days, you are getting Sunday again. After 14 days, again Sunday. 21 days, again Sunday. But we say the period is 7, not 14, 18. Of course, that is also period. Fundamental period we call 7. Similarly here, the least positive value of k, so that A power k plus 1 equal to A, that such a k is called period of that matrix. The least positive value of k is called period of matrix. This period is defined only for periodic matrices. Next. I know idempotent, now nilpotent. Nilpotent. Suppose A power k equal to 0 matrix. Suppose a matrix given A, you are finding A square, A cube, A power 4, A power 5 and so on. If you get 0 matrix, such a matrix is said to be nilpotent matrix. Suppose A power 5 is 0, automatically A power 6 is 0, A power 7 is 0. The least positive value of k is called index. The least positive value of k is called index of the nilpotent matrix. I think many of you may not know these. Normal matrix, involutory matrix, idempotent matrix, periodic matrix, nilpotent matrix. Because the words which we use, you should know it. Next. Now observe this note. Real symmetric is Hermitian. Suppose a matrix is real and also symmetric, definitely it is Hermitian matrix. Real skew symmetric is skew Hermitian. A matrix is real means the entries are real numbers and skew symmetric, definitely it is skew Hermitian. Similarly, real orthogonal is unitary. Now, if A is Hermitian matrix, then I into A is skew Hermitian. Let me give the proof of this one. Why real symmetric is Hermitian? I am taking a matrix that is real matrix, also symmetric matrix. I have shown that is Hermitian. So I am taking real matrix means when do you say matrix is real? Any one of you please? When do you say matrix is real? After going bar also? When do you say matrix is real, please? Yogi? When do you say matrix is
Yes,
real?
sir.
When do you say matrix is real?
Diagonal elements are
A
real.
bar equal to A. Very good. A bar equal to A. The equation is A bar equal to A. When do you say matrix is symmetric? When do you say matrix is symmetric?
A
A transpose equal to A.
A.
Very good. Real symmetric means I have two equations simply. I have A bar equal to A. Also I have these two equations, please. Real and symmetric. Now what I have to show? I have to show from these two equations, I should show A power theta equal to A. Means Hermitian, the word. Therefore, A power theta I am calculating. From the definition of A power theta, it is nothing but conjugate transpose. Okay. Now I have these two equations. I can replace this A bar with A. I replaced A bar with A. A transpose. Now using the second equation, this A transpose is A. Finally, I showed A power theta equal to A using these two equations. Means this equation means real matrix. This equation means symmetric matrix. I showed A power theta equal to A means A is Hermitian. Means real symmetric is Hermitian. Similarly, you can prove real skew symmetric is skew Hermitian. Real orthogonal is unitary. Next is proof of 4 I am showing to you. If A is Hermitian, Hermitian means what is my equation? When you say matrix is Hermitian, I am taking Hermitian matrix. A power theta equal to A. I am taking Hermitian. I have to show I into A means each entry of A multiply with I. Now observe. IA whole power theta. I am calculating IA whole power theta. Therefore, conjugate transpose. This I is a scalar. I conjugate is minus I because I is nothing but 0 plus 1I. Its conjugate is 0 minus 1I. Means minus I into A power theta. Because transpose won't affect on a number. Therefore, I bar A power theta. Because I is a number here. I bar is minus I. Because 1 plus 0 plus 1I, that is 0 minus I. This A power theta is A. So, IA whole power theta is minus of this. Power theta is minus of it means this IA is skew Hermitian. Whenever A is Hermitian, whenever I have this equation, means whenever A is Hermitian, IA is skew Hermitian. Why I am explaining these proofs to you is you are getting bits in gate like this. Which of the following statement is true? Which of the following statement is false? In such cases, you need not by heart all it. Once if you know the definitions, you have to verify the given equations with the, take the given equations from the words and try to get the conclusion equation. Okay, next. Okay, so far I explained the types of matrices. Now we go to the next one. Determinants. Okay, first I am explaining the second order determinant first of all. I am taking a matrix A, B, C, D. Its order is 2. I did not tell 2 cross 2. Square matrix. Its order is 2. Now, we call determinant of A, the short form det A, or Of course, it appears as mod A, but don't read it as mod A determinant of A. When you replace A with this, you get another bracket. We ignore that bracket. We simply write A, B, C, D in the notation, modulus notation. We call it as determinant of this. This use. What's this value? Please tell me.
AD minus AD BC. minus BC.
AD minus BC. What's your name, please?
Satya.
Satya. Very good. AD minus BC. Very good. Please observe a matrix given. From a matrix, you are getting a number AD minus BC. This number is called determinant of this matrix. Okay. Okay. Some of you may feel bored because I'm explaining very basics, but please realize the importance of basics here. My question here is, why this is not AD plus BC? Please tell me, anyone. Why this is not AD plus BC? Why not it is ABCD? Why not it is A plus B plus C plus D? Why it is AD minus BC? Anyone, please?
M cross N, sir.
Okay, M cross N. Okay, I agree with you. Determinant of A, why it is AD minus BC? Why not AD plus BC? I am asking. Don't you get this doubt? Your teachers explained this is determinant. So you agreed it. Why we call it as determinant? I'm asking that, please. Any one of you please know it?
Cofactor.
Cofactor. I will explain what is cofactor word also to you, please. Okay. Why this is called determinant? Please listen it. That's why I'm explaining from basics, please. Please observe it. Are you determined? Are you determined to know what is determinant? Okay. Now come to this. Our topic is linear algebra. I am taking linear equation ax plus by equal to k1. Here a, b, k1 are constants. X comma y variables. I am taking another linear equation cx plus dy equal to k2. X, y are variables. Okay. Now, this ax plus by equal to k1, it represents straight line equation. Cx plus dy equal to k2 represents another straight line equation. I need x comma y values which satisfies both the equations. Means the intersection point. Forget about matrices. I need x value, y value which satisfies both equations. Then what we do? We want to modify the sentences, modify these equations. I want to eliminate y. First, I want to eliminate y to know x value. How do you eliminate y? How do you eliminate y? These two should be same. Then I can subtract. To get same value, here I require d. Here I require b. Here bd, here bd. bdy, I can cancel. Therefore, to get d here, multiply both sides with d, the first equation. Please observe, this is implies symbol. Implies is used between equations. Please, what is an equation? Please, equation. If somebody asks you what is an equation, what is your answer? What is an equation? Always you write equations. What is an equation? If somebody asks you, when you go to interviews, you may be asked like this, please.
Left hand side equals to right hand side, sir.
Left hand side equal to right hand side. Okay, you try to attempt the answer. You can simply say like this. Any expression containing the symbol equality is called equation. Simple. Any expression containing the symbol equality is called equation. Suppose if you don't have equal to k1, ax plus by is not equation. Okay. Now this is another equation. Between equations, we use implies symbol. From this equation, you are getting this equation. Means you can think it is just like simple balance. Both sides you are doing multiplying with the d. Okay, both sides you can do it. Now, similarly, to get b dy, multiply the second equation both sides with the b. You are getting a new equation from this, multiplying with the b. Now, subtracting second equation from first equation, this b dy cancels. You know, adx minus bcx, take x cancel, subtracting, you will get adx minus bcx, which is ad minus bc into x. These two get cancelled. I'm writing single equation from these two. Equal to what? K1d minus K2b. Therefore, x value is this by this. K1d minus K2b by AD minus BC. Similarly, you can calculate y value. You will get this. Now, observe this. I need x comma y values which satisfy both the equations. Here A, B, C, D, K1, K2 are constants. If you observe, here AD minus BC, here AD minus BC. Suppose this AD minus BC is 0, what happens? What about x value then? Suppose AD minus BC is 0, what is x value?
Infinite.
Infinite means it is not real, please. Infinite is not real. I need real number. So, when this AD minus BC equal to 0, these two lines are parallel. Tell us this. Tell us this. But when AD minus BC is 0, these two lines are parallel. You means it is not possible to find x comma y values which satisfies both the equations. When AD minus BC equal to 0, these two lines are parallel, means it is not possible to find xy values which satisfy both the equations. Therefore, this AD minus BC determines whether the equations has a solution or not. If you are asked to find xy values which satisfy equations, immediately we calculate AD minus BC. We observe AD minus BC. Suppose AD minus BC is 0, you cannot find solution here. Therefore, AD minus BC determines the solution of the equations. Whether solution is there or not, AD minus BC tells us, it determines. Hence, this is called determinant. I think you got the meaning. AD minus BC determines whether the equations has solution or not. So, this AD minus BC, this number is called determinant. Okay. Next. The same concept, third order. Now I am using the notation, subscript notation, because if I go on writing A, B, C, D, E, F, I may stop with Z. So I can use numbers. A11, A12, the standard notation. What is the determinant of this? Please observe the same concept. If we have three equations with the three unknowns, ax plus by plus cz equal to k1. Similarly, other two equations. Eliminate z from first two equations. Eliminate z from second or third equation. Finally, you will get two equations xy. Eliminate y. Finally, you will reach x value. Similarly, you can find y value. Similarly, you can find z value. The denominator remains same in all x, y, z's. The denominator is called determinant. How do you remember the determinant? Using this notation. This AD minus BC we remember like this. Three equations, three unknowns. When you solve, the denominator remains same. That denominator is denoted like this. Now tell me this determinant. Now observe. This determinant you can express in many ways. For example, using the first row. Using first row, I am expressing the determinant with the different columns. This is A11 into Determinant of this second order, please. A11 into determinant of this. Of course, you write A22 into A33 minus A32 into A2, AD minus BC. A11 into determinant of this. Next, I am taking this here. Minus A12 into determinant of these. Minus A12 into determinant of these remaining. Next, I am taking this here. Plus minus plus. Plus A13 into determinant of these. Of course, this is familiar to you. I calculated the determinant using the first row. With the help of first row, I calculated. Using the first row. Now here, AD minus BC, AD minus BC, AD minus BC. Finally, you will get a value. This value is called determinant of this third order. Okay, this is usual practice to you. Now, to find determinant of a matrix, you need not use always first row. You can use second row or third row, or you can use first column, second column, or third column. You can use any row or any column to calculate determinant. For example, the same determinant I am using to calculate, I am using second column. For example, I am using second column to calculate determinant. This column I am using with the different rows. With the different rows. Here, the sign is minus, plus, minus, plus, minus. Because minus 1 power 1 plus 2, negative. Minus 1 power 2 plus 2, positive. Minus 1 power 3 plus 2, negative. Therefore, negative, positive, negative. Therefore, using this column with the different rows. Therefore, minus A12 into these four elements, determinant of these. Minus A12 to the determinant of this. Next, using this column, coming to next row. Using this column. Plus A22 into these four, the corner four elements, determinant of this. Next, using this column. Minus, plus, minus. Minus A32 into these four elements. This is also determinant of the same matrix. If you observe, using R1, the middle one, using C2, the first one, these two remain same. If you calculate the first and last, here the last two, it remains same because these two are equal. Like this, you can calculate third order determinant in 6 ways, using first row, or using second row, or using third row, or using first column, or second column, or third column. You can evaluate the determinants. You need not use always first row. Okay, next. The same concept I am extending to the next fourth order determinant. The standard notation I am using, fourth order determinant. For example, I am expressing this using first row with the different columns. This is A11 into determinant of this third order, please. A11 into determinant of this third order. Next, take this here. Plus minus A12 into determinant of this remaining. Minus A12 into these. Next, take this here. Close this third column. Plus, minus, plus. Minus 1 power 1 plus, which is plus. Plus A13 into remaining. Plus A13 into remaining. Next, to take this here, the last column. Minus A14 into this one. Minus A14 into this. This gives the determinant of this fourth order. Okay. Now, if we expand this third determinant, these four third order determinants, you will get this fourth order determinant. Now, my question here is, how many terms are there in the right side here? Term is separated by plus or minus after expanding. If you have second order, how many terms you will get? In second order, how many terms do you get in determinant?
2 terms.
AD and BC. AD minus BC, of course. In third order, how many terms do you get? In third order.
3 terms.
Huh? In third order.
3 terms.
No. 6 terms, please. Why? Please observe it. Let me show this. In second order, you are getting 2 terms. In third order, you are getting 3 second order determinants. Here 2 terms. Each term into A11 means 2 terms only. Here 2 terms. Here 2 terms. Third order determinant, you are expressing 3 second order determinants. Each second order determinant gives 2. Hence, 2, 2, 2. 3 into 2, 6 terms. 3 into 2, 6 terms. Similarly, in fourth order determinant, each third order determinant gives 6 terms. Therefore, 4 third order determinants. How many terms total? Now tell me. The number of terms I am asking in fourth order.
24.
24.
24.
Very good, very good. How you are getting that 24? 4 into third order. 4 in third order, 4 third order determinant. 4 into in third order, 3 second order determinants. Okay. In fifth order, how many then? If you expand like this, how many terms are there in fifth order?
120.
120. Very good. Suppose the order is n. In nth order, how many terms are there?
N into M terms.
Factorial.
Very
N
good. N
factorial.
factorial. Okay. Very good. Very good. It is not a formula. You got the concept like this. Okay. You should learn the topic like this, not to by heart. Therefore, a problem given. The number of terms in the expansion of nth order determinant is n factorial. I think got this meaning. The number of terms in the expansion of nth order determinant is n factorial. Yeah. Okay. If you learn the topics like this, you never forget. Also, you will know how to apply it. Next. Now, minors. I think all of you are minors. You are in first year, below 18 years, or just you are becoming majors. What is a minor? What is a minor? Any one of you? What is minor?
Smallest values.
Smallest means the person whose age is below 18. Similarly, here, minors are not the people, minors within the matrices I am talking. Okay. Observe it. Mij. I'm explaining minors for third order. Minors for third order. Okay. M11. M11 is one minor of this matrix. What's that minor? Let me show. M11 means it just close first row and the first column. And the remaining is second order determinant is called minor. If you write it is a matrix, it is submatrix, please. It is a submatrix. But its a determinant is called minor. This minor we denote with M11. Let me show another minor. M23. M23 means, what is M23? From this A, the children of this A, you can think like it. Minor of this. Close second row and third column. Close second row. Close it. And close third column. The remaining submatrix determinant means determinant of the remaining arrangement. This is called another minor. Means at each place you are getting one minor. Means you have 9 places, you will get 9 minors for A. 9 minors of order 2. Next. Okay, somebody used this word cofactor when asked why it is determinant. Cofactor. What is a cofactor? Now tell me. Cofactor. What is a cofactor? Anyone knows? What is a cofactor? Minus of matrices, cofactors of matrices now. These are nothing but Cij minus 1 power I plus j into Mij. Minus 1 power I plus j into Mij. For example, C11 is M11 only. Please observe why. Minus 1 power 1 plus 1. Minus 1 whole square. Therefore, C11 equal M11. Now tell me what is C23? What is C23?
Minus M23.
Very good. Minus M23. The reason? Minus 1 power 2 plus 3. So these are also determinants. These are also numbers from matrices. What do you observe the difference between minus and cofactors? Minus are determinants, cofactors are also determinants, but with size plus and minus. So you can think like this: minus are children. Minus are children. Cofactors are children, but with gender also, plus or minus. I think you got it. You can think like it. Minus are children. Cofactors are children with together with male or female. Okay, plus or minus. Next, adjoint of a matrix. It is another operation. Input A, output a new matrix. Adjoint of a matrix. This is nothing but transpose of cofactor matrix. Transpose of cofactor matrix is called adjoint of a matrix. Suppose this matrix A given. Adjoint of a matrix is an operation. Transpose of a matrix, conjugate of a matrix, conjugate transpose of a matrix, adjoint of a matrix. These are the operations. Here A is the input. The output is adjoint of this matrix. It's another matrix. That is nothing but transpose of cofactor matrix. Now this is, we denote with adjoint here. Now observe. Here C11, C12, all these 9 you can calculate with signs. C11, C12, C13. Write it as column because transpose, please. Transpose. Cofactors matrix with transpose. C11, 1, 2, 1, 3. Actually, C11, C12, C1. That is cofactor matrix. It's transpose. Okay. Whenever a matrix given, calculate minus and put the signs. Means calculate all the C11, C12, C13, C33. And arrange like this, you will get a new matrix from this matrix. This is called adjoint of this matrix. Now, a theorem. If A equal A is a n cross n, means order n square matrix, then A into adjoint A equal to adjoint A into A equal to det A into in. Unity matrix of order. Yeah. A is the given matrix. Adjoint A new matrix obtained from the entries of A. Now, input output. These two, if you multiply, in general, AB, BA need not equal, but AB equal BA are same when B is adjoint A. In matrices, A into B, B into A need not equal. But AB equal B is right when B is adjoint A. And this result also we can tell. That result is nothing but determinant of A is a number obtained from this matrix into unit matrix. Scalar multiplication. Let me show for your clarity in third order. Now this meaning A is this one, please. A is this one. Now adjoint A is this one, this matrix. Adjoint A, this matrix. Yet these C's are obtained from this. This result is A into adjoint. It is same as adjoint A into A. The result is det A into I3 here. Det A into I3. Here triple ones becomes det A's. 0 into det A, 0 into det A. Always. I think got it. You have to visualize this theorem like this. A into adjoint A is det A into I. Okay. Now, here you can think like this. A is a matrix. Its children, the minors, with gender plus or minus. The children join together forms a big matrix called a joint. They join together and formed another matrix called a joint. The children formed another matrix. After forming this, what they did is they fight with the grandfather A. A into adjoint A into, they clash each other. When they clash each other, what happens? All died except the diagonal. Please observe it. Getting like it. The matrix, its children with the genders, they join together, form a new matrix called a joint A. After forming new one, they fight with their grandfather. What happens? All died except the diagonal. The diagonal is dead. A. Next. Inverse. Inverse. If AB equal to BA equal to I, suppose I have two matrices whose product in either order is same and the result is I, then this B is called inverse of A. Just like x into 1 by x equal to 1. X into 1 by x. 1 by x means inverse of x with respect to multiplication. This B is called inverse of A. We denote like this. We read it as inverse of A. If AB equal to BA equal to I, then this B is called inverse of A. Means a matrix given. Find another matrix so that the product is I. Please observe, if two matrices given, it becomes easy to find the product. But one matrix given, another matrix B not given, but the answer given I. Find this matrix. A into what matrix gives unit matrix? That matrix is called inverse. To find this inverse, we use this theorem. If you observe, A into adjoint A by det A is same as adjoint A by det A into A equal to I. Therefore, in place of B, you have adjoint A by det A. In place of B means this A inverse is nothing but adjoint A by det A. This is obtained from this theorem actually. Adjoint A by A inverse equal to adjoint A by det A. Singular. A matrix is said to be singular if its determinant is 0. So not singular. Okay. Non-singular. A matrix is said to be non-singular, not equal to 0. Determinant not equal to 0. Okay. These are the words which you have to remember. Next. Properties of determinant. Properties of determinant. The first one, det A equal to det A transpose means A and A transpose determinant remain same. A and A transpose need not equal. If they are equal, we call symmetric matrix. If they are not equal, it is not symmetric. But the determinant remains same. The second, interchange of parallel lines means parallel means interchange two rows or interchange two columns, but don't interchange a row with a column. For example, the determinant of this one, when interchange any two parallel lines, for example, I interchanged this second and third rows, then you will get minus of the determinant. Please, minus of the determinant. The first row remains same. I am interchanging A3, B3, C3. Now A2, B2, C2. The given matrix determinant, I interchange second and third rows. Then you will get minus sign. The reason is very simple, because when you expand the first one using first row, the left side using first row, A1 into B2C3 minus B3C2. Whereas the right side A1 into B3C2 minus B2C3, you are getting reverse. It's minus half you are getting. Similarly, the other two terms also you get minus sign. That's why when you interchange any two rows or any two columns, you should put negative sign. Next. Same parallel lines. Same parallel lines. For example, these two are same. The determinant is 0. A2, B2, C2, A2, B2, C2. The reason is very simple. A1 into B2, C2 minus B2, C2, which is 0. P1 into A2, C2 minus A2, C2. Similarly, C1 into A2, B2 minus A2. When any two parallel lines are same, the determinant is always 0. The next one. Multiplication in a line, please. Line means either row or column. Suppose a line means here in a row is multiple of k. You can take k common in a determinant, please. You can take k common from a determinant. The reason is very simple. When you expand the left side, ka1 into b2c3 minus b3c2. Next, minus kb1 into, next plus kc1 into. Write that k outside. Therefore, you can write k outside in a determinant. From any line, you can take common from row or column. Next, the fifth one. Addition in a line. Suppose in a determinant, a row or column is sum of two numbers like this. This can be written as sum of two determinants. Ignore these b's, write the determinant. Ignore these b's, write the determinant. Plus, now ignore these a's and write the determinant. Here the first column A1, A2, A3. Here the first column B1, B2. Remaining two are same. Therefore, if your row or column is sum of two elements, that can be written as sum of two determinants. The reason is simple. Suppose if you expand the determinant using first column, A1 plus B1 into C2 D3 minus C3 D2. A1 plus B1 times. Therefore, here A1 times this one. Here B1 times this one. I think you got it. Next. I put triple star property. C1 plus KC2 plus LC3. C1, please, the coefficient is 1. C1 plus KC2 plus LC. Its meaning. Here small c means entries, here capital C means columns. I am replacing the first column, with the first column replaced as first plus k times second plus L times third. The first column replaced like this. First plus k times second plus L times third. The second and third columns as it is. Okay. Now these two determinants remain same. Why these two are same? Observe it. The right side can be written as sum of three determinants using fifth property. This can be written as sum of three determinants, in which the first determinant is A1, A2, A3, first column, second column B1, B2, B3, third column C1, C2, C3. Means you are getting left side. Now the second determinant, KB1, KB2, KB3, B1, B2, B3, C1, C2, C3. In the second determinant, take K common. Then B1, B2, B3, B1, B2, B3 remains same, hence it is 0. The second determinant contributes 0. Similarly, the third determinant contributes 0 after taking L common. Means, after writing the right side, sum of three determinants, the first one is left side only, second one is K into 0, third one L into 0. That's why whenever you are simplifying the determinants, you are using operations like this, C1 plus K, C2 plus LC. Usually we won't use L, simply C1 plus K, C2 type. Of course, you can use row operations also, but don't use KC1 here, please. The multiplier, wherever you are replacing, that coefficient should be 1. I use a triple star property because it is a combination of the previous 3 results. Sum of this fifth one, writing as sum of 3 determinants, and then taking common, and then 2 or same is 0. Therefore, 3, 4, 5 combination is the 6th property, frequent to use in problems. Det AB equal det A into det B. Means our determinant of product of matrices is product of determinants. Please observe, in words, determinant of product of matrices is same as product of determinants in the given order. Automatically, because det A and det B are numbers, therefore det B into det A also you can write, because both are numbers. That can write as det BA. Therefore, det AB equal det BA, right? But AB and BA need not equal. AB and BA need not equal, but the determinants remain same. Determinant remains same. Next. Det KA, K power n into det A, where A is of order n. Please observe, K into A means all the entries of A multiply with K. All the entries of A multiply with K. It's a determinant. K power n det A. The reason all the entries multiply with K, from first row take K common, from second row also take K common, third row take K common, like this from nth row also take K common. So K power n times det A, please. Det K is K power n det A, not K into det A, please. Where A is of order n. Okay. These are the properties of determinant. Next, small definitions. Of course, these are familiar to you. Equality. When do you say two matrices are equal? Any one of you, please? We know that 6 by 3 equal to 2 by 1. 6 by 3 equal to 2 by 1. Similarly, when do you say two matrices are equal? Any one of you? Please. When do you say two matrices are equal? If the corresponding entries are equal, if and only if Aij equal to Bij for all I, j. The corresponding entries should be equal. Next, addition. A plus B. The corresponding entries addition, please. Corresponding entries addition. Subtraction. A minus B. Aij minus Bij. Automatically the order should remain same. Scalar multiplication. K into A equal to K Aij. Means all entries of A multiply with K. Next, the multiplication. Before going to multiplication, let me give examples for this. A equal to this, B equal to this. I am giving an example. Are they equal? Anyone of you, please? A equal to B. Does it right or wrong? Anyone of you, please? Please respond.
Wrong, sir.
A equal to B. Why it is wrong? Tell me.
Corresponding elements not equal.
Right, very good. If at least one entry with the first 2 equal to 1 wrong. Therefore, A equal to B wrong. What is A plus B? Now tell me. A plus B. What is A plus B? Please. A plus. I may ask simple questions, but please B.
3,
3, very good.
3 minus 2, 6.
Right, very good. A plus B, right, very good. What is A minus B?
1,
1,
7,
7,
minus 10,
minus 10,
minus 10.
0.
Very good. Very good.
0.
Very good. What is 2a? What is 2a?
4.
10 minus
4,
12,
10,
6.
minus 12, 6.
Very good. Very good. Okay. Now, please. Now, AB. AB. Please let me explain. Is equal to this. Okay. Are you okay now? Are you okay? Do you agree?
No, sir.
No, no. Am I wrong? Okay, you are not agreeing. Okay, okay, okay. I will come to you. Okay, now tell me first, A plus B, does it right or wrong? A plus B, does it right or wrong?
Right, sir.
Yes,
Right.
right, sir.
The reason 2 plus 1, 5 minus 2 like this. What is A minus B? Does it right or wrong?
Right.
Right, very good.
Right, sir.
What about 2
Right,
into A?
sir.
Right. What about AB?
Right, sir.
AB?
Wrong.
Wrong. I don't agree because 2 plus 1, 3. 5 minus 2, 3. Similarly, 2 minus 1, 1. Like this. Now AB, 2 into 1, 2. 5 into minus 2, minus 10. Minus 6 into 4, minus 24. 3 into 3, 9. Okay. What's that? What's wrong with me? Please. When I'm telling addition, you are telling right. A minus B right. 2A right. Why you are finding fault with me, please? The same I did. The same I did. Please tell me why it is wrong. Why you are telling wrong to me? Any one of you, please? The same I did as addition, I multiplied. The notation is also similarly addition, multiplication A into B.
It's right, sir.
Huh? Right, huh?
wrong, sir.
No, sir.
Uh,
Wrong, sir.
why this is wrong, I am asking. What is correct then?
The elements should be multiplied now.
First row and first column.
First row, first column. Okay. Huh? I should not multiply like this. Okay. Huh? Don't you get this doubt when you are learning in lower classes? In lower classes, addition, okay, multiplication, simple. If it is defined like this, it becomes very simple to us. Okay, got it? But our teachers explain not like this, row column wise. Why they explain row column wise? Why not this? Why this is wrong? You are telling wrong. Okay, I agree with you now. Why this is wrong? Tell me. Anyone knows? Because our teachers explain multiplication is row column way. That's why we did it. Huh? I am explaining ordinate way. You are telling wrong. Please, you should know why multiplication is defined row column wise, not ordinate wise. If you don't know why row column wise it is defined, how can you apply these matrices in calculations? It is shorthand language. Arrangements we denote with the symbols, and we do calculation with the symbols. Shorthand language. How do you know the shorthand language? Without knowing why AB is not like this. Got it? Got my point? Okay. I will explain why AB is row column wise in my next section. Okay. You will realize if you know the fundamentals of the subject, you can answer any question given in examination, in GATE examination. not only GATE, you can apply this mathematics subject anywhere. Okay, I'll explain those also. Probably in my next section, I will start with the GATE questions also. Okay. Any doubts? If you have any doubts, you can ask. I just started the introduction. Of course, sometimes many points which you know it, some points you may not know it, even in basics. I think you may not know it why AB is defined like this. I'll explain to you in my next section. If you have any doubts, you can ask.
You can ask me if you have any doubts.
Anyone, please?
Okay, sir. Students బాగా అర్థమైనట్టుంది సార్.
అంటే I start with the very basics, in fact, actually.
Yes,
Basics
yes,
నుంచి చాలా fundamentals నుంచి.
అవును సార్.
సో డిటర్మినెంట్ అంటే ఎందుకు అంటారు అని తెలియదు చాలా మంది. అంటే డిటర్మైన్. అలాగే నెక్స్ట్ వచ్చేసరికి ఇక్కడ ఏబి ఎందుకు అలా డిఫైన్ చేస్తాడు ఇన్ మై నెక్స్ట్ సెక్షన్ ఐ విల్ ఎక్స్ప్లెయిన్. Later I come to the GATE questions also in my next section. Okay, the first session, that's why I am a little bit slow to adjust with the students. That too online, that's why I am very slow.
Okay, sir. Okay, sir. Thank you, sir.
Okay, thank you.
Ma, students, test is the same times, with the same link, ma. Hello?
Okay, ma'am.
Yes, ma'am.
Okay, ma'am. Yeah,
ma'am.
sir, continue the same topic, ma. These GATE questions also sir will explain for you. Kapiti, ఇప్పుడు సార్ క్వశ్చన్ అడిగే కర్మ డిటర్మినెంట్ ఎందుకు ఇలా చేయాలి ఏంటి వాట్ ఈస్ ద రీజన్ ఓకే kapiti నెక్స్ట్ క్లాస్ మాక్సిమం అటెండ్ అవ్వండి మా ఓకేనా థ్యాంక్ యూ మా ఓకే థ్యాంక్ యూ సో మచ్
Okay, ma'am.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.